is it? Okay, I'm talking to myself. Okay, now. Okay, good morning again. That's why the host didn't say anything. Okay, so what we have done, thank you, Darshini, for letting me know that I'll just talk to myself. Okay, so what we have done last week, we have conducted the first factorization where we did on the um, what we call it, we use enzyme called sucrase, okay, also known as invertase. So this sucrase will react on the substrate called sucrose in the presence of water to form glucose and fructose. Okay, so I'm going to share the screen with you so that we can see everything together. Okay, so this is what we have. We have the enzyme called invertase or sucrase. Where's the, yeah. The enzyme name is invertase or also known as sucrase. So this enzyme will react with the substrate, which is sucrose, in the presence of water to form glucose and fructose. So what we did basically, we are measuring the glucose. We're measuring the glucose. Okay, that's why we will have the glucose standard. Okay, so our first activity was to determine the enzyme activity versus enzyme concentration. Okay, so what we did, okay, we have test tube A until test tube I. A until H, we can see the pattern, okay, the pattern of the standard is increasing. No, not standard, I mean the activity. So we can see from the graph, once you have plot the activity, you can see that we have this kind of increment. And then when we reach a little bit at the top, it's just like slow. You can see at this point, the activity become slower. Yeah, I mean this point. Yeah, this point where at absorbent, where the concentration we use for the invertase enzyme 25 2.5 microliter and 3.0 2.5 mil and 3.0 mil of invertase. So what will be the concentration of invertase for tube G, please, and tube H? Someone? What will be the concentration for tube G and H? Put it in the chat room. Okay. Look at your table, your report. What will be the concentration? Okay. So it is 0.08 gram per liter. Okay, it is 0.08 gram per liter. 0.08 gram per liter. Okay, and the H will be 1 gram per liter. Okay, so we have this 0.821. Okay, So why do you think that that the absorbance for G and H is not that much different compared to the others? Okay, so basically what happened at this time, 0.08 gram. Okay, it's 0.1. Okay, sorry. How do we can going to, okay, it is 0.1 gram per liter. Okay, so basically what happened at this point in between 0.08 gram and 0.1 gram per liter. Okay, what happened at this time, the rate of reaction is not as high during this middle part. Okay, this is due to we have the substrate limitation here, where when we have the effect of enzyme concentration, okay, enzyme concentration, okay, in milligram per mil versus the relative activity. Okay, so what happened at this time? We can see that if we keep increasing the enzyme concentration, the product will just become plateau. It will not increase the product. Okay, the product will be just like this towards the end. You know? Okay, because this is where we have this is what we have. We have here, it is called the maximum velocity. We cannot say the Vmax, because if you want to say this is Vmax, up here should be the substrate. So, but now we have a very limited substrate. So at this time, at this point, at this position, we do not have enough substrate. We do not have enough substrate, so that if we keep increasing the enzyme concentration, the number of product formed will be just the same. This is because substrate here will become the limiting factor. Okay, so I'm going to type this. Substrate become the limiting factor. Okay. 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 Substrate become the limiting factor for this experiment because we do not have enough substrate where we have more enzyme inside here. Okay. Okay. So for this case, yeah, substrate will be the limiting factor. Okay. So what happened to tube I? We have also tube I in here. So I in here, like we have discussed earlier, it is a T0. It is called T equal to 0. Why T0? Because we have used the dead enzyme. Okay, the enzyme that we have killed earlier. We killed the enzyme earlier by incubating the enzyme at 100 degrees for 20 minutes. Okay, something that can be discussed. Okay, something that can be discussed in here, because when you look at this picture, this video, yeah, when you look at this video, you can see, okay, okay. So starting from tube A until I, okay, so the tube I still giving some reading. Yeah, of course it will give reading because our blend is the water. Okay, but the reading is much higher than tube A. Okay. And then tube B, right? Because the reading here, we got 0.0778. Okay, and then the reading for B is around 0.057. So the recommendation for this side, we can just say that 100 degree for 20 minutes may not be sufficient enough to kill all the enzyme. Okay, so what we can do to make sure there's no activity for tube I, we can suggest we can just incubate more than 20 minutes. Okay, incubate the enzyme more than 20 minutes so that by the end of the day we can get T0. Okay, the reaction did not happen because we have already killed the enzyme earlier. Okay, so is it okay for that part?
Doktor, so if P0 maksudnya yang tube I should be clear.
Yeah, tube I supposed to have similar reading to tube A. Okay, tube I supposed to have similar reading to tube A. Okay, so yeah, but yet what we have, tube B, yeah, of course, tube B will have some reading because we have put little bit of the enzyme. So this a little bit of enzyme will make reaction with the substrate. Okay. Yeah, and that we have 0.057. But this I, we have 0.078. So for this case, supposedly I will not give you any of the activity. Okay, so but still, if you want to consider this as your control, yeah, you can, because this control mimic the whole thing. Okay, the whole thing. You know, tube I and H, they are similar composition. 3 mil of enzyme, 3 mil of that enzyme. Similar composition of the substrate, and then the way you incubate, the way you kill it, they are the same. Okay, by incubating at 100 degree, we react at 55 degree. So what happened is obviously different because in H we have got, what is the reading for H? Someone, you still remember what is the reading for H? Absorbent. I mean absorbent for H. Okay, so H is 0.776. So you see, by having the dead enzyme, obviously, so the reaction will not occur because the enzyme is already dead. But I'm not sure that 20 minutes is sufficient or not to kill the whole enzyme. Okay, that's why we still have some. This reading is much high, a little bit higher than this reading, where we have a little bit of the enzyme, I mean active enzyme. Okay, so we will learn about thermostability later in this experiment. That it makes sense why we need to kill longer for this one. Okay, so is it okay now? I will move for the next experiment. Okay, so that I will just scroll down a bit. Okay, so now you hopefully you have filled up everything this side. Okay, okay, is that a problem to take tube A as control. No, you can use tube A as a control. Yeah, you can. Okay, in fact, sometimes we need to make up a control. How? Okay, tube A having no enzyme. Okay, but the good thing of having I as your control, okay, it is because, for example, if you are working with a culture, that culture use okay, if this culture, I mean that, okay, you have this culture. I'm going to go to sketch of last year. Okay, so you have this culture, and then what happened inside this culture? You have the enzyme inside. Inside this culture, normally the broth, I mean the broth to grow your culture, to cultivate your culture, normally it is like yellowish color. Okay, yellowish color, something like that. Okay, so if the broth is already yellowish in color, okay, you will end up having some bleeding because of the yellow color from the broth, not because of the glucose formation. Okay, so because of that, okay, sometimes we need to use tube I as the good control. This is a really good control. Okay, so why here? Because inside this, from the broth where you have your culture inside, you will need to kill first. Okay, if you kill the enzyme, the yellow color still will be there. Okay, the yellowish color of the broth still will be there, but you kill them earlier. You kill the enzyme earlier inside the broth. So this one, the T0, okay, will carry the yellow color of the broth throughout the experiment. Okay, I repeat, if your experiment, you are working with extracellular, okay, we're talking about extracellular expression, extracellular, okay, extracellular enzyme, okay, where the protein, where your enzyme will be secreted in the culture medium. Okay, if you have a cell, here, okay, this is the DNA, and then this is the protein, and then the target protein now it's being released into the medium where your target protein is no longer being, I mean, be placed inside the cell. It is being secreted. So once your protein is secreted to the cell, to the environment, that means your protein now is inside the broth, right? For this case, you don't have to break the cell. Your protein is inside the broth. But we need to bear in mind that the color of the broth itself is already yellow. Even though you have your culture or not, the color of the broth still will be yellowish. So we don't want this yellowish color of your broth interfere with the real reading of the activity, where your activity can be formed because of the glucose being released. Okay, so that's why for this case, this will be a really good control, where your extracellular broth or your broth itself, you can just assay. Okay, that means the yellow color here is because of the broth. We can minus this. We can deduct this. Okay, so is it okay, Toba? Okay. So now we move to the second part. Okay, so now we have here effect of substrate concentration. It will be almost similar to the previous experiment. So now we are going to label the tube. Okay, so when we have the effect of substrate, that means we need to have some idea that our graph will be like this. Okay, it will be substrate here. Okay, and then we are going to have here the product, the P here. Okay, the product here. The product here, okay, you can measure in terms of unit per mil or relative activity. Okay, so if we have the substrate concentration, oops, okay, the graph, okay, will be just like this. Okay, so yeah, we need to consider that our enzyme is just ES formation. Okay, we can measure the product, but we are also measuring the E combined with the S. So we have E plus S, so it will form ES, and then we get the P, the product. So we're measuring the product, and then this combination is because of the E and S. We have for this case, we have a very limited E. We do not have enough E for this case. Okay, for this experiment, we will find that the E is not enough. Once we have increased the substrate concentration, but the number of E is just like that. Okay, for this case, we have used 3 mil of the invertase. I think this one will be similar like before. We have 1 gram, right? Yeah, we have used 1 gram. Is it 1 gram from previous one? Let me check. Yeah, we have used here 0.2. Okay, for this case, we have used 1 gram per liter of invertase. So if 1 gram per liter of invertase, what will be the final concentration of invertase if you have used this 3? So what will be the final concentration of invertase if we have used 3 mil? Okay, it will be M1V1, M2V2. Okay, M2V2. So the total volume, okay, the M of this will be 3 mil. The volume is 6. Okay, the M2 will be unknown. Okay, and then the volume, no. This one will be 1. Okay, sorry. This is 1. Okay, 1 gram per liter. And then the volume here we take, okay, this is 6. This is 3. Okay. So M will be what? Okay. Okay, Albana. Really? 0.5? We have taken, okay. So, okay, done. You get this 0.5. Okay, I'm going to stop this. Okay, now you have 0.5, which is higher. Okay, we have fixed. We have fixed, oops. We have fixed invertase, which is 0.5 milligram per mil, okay, of the invertase. Okay, so now we will have this kind of graph because we have the increase of the substrate, and then the P here, the product here. Oops. Okay, so here what we can observe, we can see here that we have here the Vmax. Okay, this side we can call it as Vmax. We have the maximum velocity at this side because the enzyme become the limiting factor. E is the limiting factor. Okay. E become the limiting factor for this experiment. We do not have enough enzyme to hydrolyze a lot of substrate here. So I know that you have in mind that enzyme is reusable. We can always, keep reusing the enzyme for multiple reaction. I know, but for this case, since we have only having reaction for 5 minutes, okay, so we know that the enzyme will use the substrate only once. Once the ES form and then it form product, that's it. Okay, so now for our case here, for this graph, Vmax, we have the maximum product here called Vmax, and then against the substrate. Okay, you can calculate the substrate concentration, the sucrose concentration by using similar formula, so that you will have each of these with different substrate concentration. Okay, so that this substrate concentration can be placed for the x-axis. Okay, for the p-axis, you can use the unit per mil, which has been converted to relative activity. Okay, so if we have Vmax, okay, Vmax divided by 2 here, that means we know the Km, okay, Michaelis Menten constant for this enzyme activity. Okay, so is it okay here? Previous activity, okay, in the A experiment, now it is B. Now it is B, okay. For the first one, we did the effect of enzyme concentration. Now, the second experiment, effect of substrate concentration. Okay, if we have substrate concentration back here for the x-axis, we can plot for the Michaelis-Menten constant. Okay, right? So, any question for this side? For this, you don't have to prepare, but you can always practice, make yourself familiar with this, practice so that you know, just by looking at it, you know this is the final concentration of the sucrose when we have different sucrose concentration with the constant invertase amount. Okay, so any question for this part before we move for the second experiment? I mean, not second experiment, the third experiment. How do we get the y-axis? Y-axis, we can get the y-axis just similar way. Okay, similar way to the one we got it here. Okay, similar experiment. Okay, where we did the assay, we put everything. We put everything, all of this incubate at 5 degrees for 5 minutes at the NSA, boil in 100 degrees for 10 minutes. Oh, okay, the relative activity. How do we get the relative activity? Okay, so for this one, we know that you will get the unit per mil. Okay, unit per mil. For the last one, you will have here, for example, 3 unit per mil. Okay, so just convert this, put it in the standard, then you will get the activity, right? Okay, so for tube B, maybe you have 6 unit per mil. This one 12 unit per mil. Okay. Okay, maybe this one 16, 20, 21, and then maybe 21.5, something like that. Okay, so what happened? The highest activity for this is 21.5. How do we get relative activity? It's by dividing the current activity. Will you give absorbent reading? We have not done this experiment, but the absorbent will be almost similar to the one that you get from the previous experiment. Okay, the experiment, the absorbent here, you will get the absorbent almost similar to the first experiment, to the experiment A. Okay, it will be similar. Okay, so that's why I didn't do this experiment because it's almost similar, except the way we interpret it will be a bit different. Okay, so now we go back for this one. We have 21.5. Okay, 21.5. We need to divide by the highest activity, which is 21.5, and then multiply by 100. Then we get 100% because this is the highest activity. Okay, for this 21, okay, for the second relative activity, 21 divided by 21.5 multiply by 100. Then you get the what we call it, the relative activity for this. So what's the relative activity for 21? Okay, 97.67%. Oops. Okay, so what the relative activity for this 3 unit? So it will be 3 divided by 21.5 multiplied by 100. It will be, yeah, it will be 14. Okay, 14%. Okay, yeah, 13.95. Okay, so it will be 13%. Okay, 14%. Then you know this is 100%. This one will be 97.6%. 97.6%. And then this one will be 14%. Then now you have got your relative activity. Rather than you are presenting the unit per mil. Right? So you will have a good data. I mean the way you present it by having relative activity. So your graph will be like this. So the P will mean the activity. Okay, so you can label it as relative activity. So relative activity, okay, in percentage versus substrate concentration. Then you will have something like this, 100%, and then this one will be 14%. Oops. The lowest one, the lowest one will be 14% around here. Okay. So the pattern you can see here, as we increase the color of the essay will just like this. You know, like, okay, as we increase the substrate concentration with the constant enzyme amount, the rate of reaction or the product formation will be increasing. Towards the end, these two tubes will give you, towards the end, these two tubes will give you not so much different because it has reached the maximum velocity, the Vmax, okay, the maximum velocity. Okay. Okay. Shall we move to the next one? Okay, guys, I will move. Okay, so meeting end in 2 minutes. Let's just wait for the second batch. We can just sign up and then go for the second session of the recording. Okay, I'm going to get myself ready. Okay. So